Hello, everyone. Today, we will continue discussing our topics in electromechanical devices. So the topic today is power transformer. So we will start in this topic today. It may take uh, like around 5 classes, and this is going to be a single material. I will share with you the material updated with our handwriting on eCampus. So the objectives of these materials will be reviewing the equivalent circuit of the practical transformer. So one of the topics I taught in electrical circuits too is single phase transformer. I know some of you guys didn't take all of the details of the single phase transformer in electrical circuits too. For that, we will elaborate more in the details of circuit of the single phase transformer. And then we will start in the three-phase transformer just to review your refresh your memory and review the single-phase practical transformer, and then start in the three-phase transformer. Then to drive the equivalent circuit of a three-phase transformer. We discussed before, guys, the meaning of equivalent circuit in the magnetic circuits topics. So we need to make equivalent electrical circuit for our transformer for a three-phase type. Then another object is to understanding the different connections of three-phase transformer bank. So we have what's called three single-phase transformer. We have what's called three-phase transformer. So what's the meaning of transformer bank and what are the different connections? So we will discuss all of these connections together and when we need to have the different connections in the applications, and finally analyzing the transformer efficiency and voltage regulation. So these are two evaluating parameters for transformer, for power transformer. So we will analyze the performance of the three-phase transformer and calculate these terms, the transformer efficiency and the voltage regulation. So as an introduction, firstly, guys, what is the transformer definition? So we can say transformer is electromagnetic device. So it's not electromechanical device because we don't have mechanical elements moving in this device. Why we are discussing such a device in electromechanical devices course? Because electromechanical is referring to electrical machines in general. Okay, so it's not specifically the devices that have mechanical parts or motion. However, this is referring to electrical machines, and one of the most important electrical machines used in industry is transformers. So it's not electromechanical device, it's electromagnetic device because we don't have mechanical parts, and it's used to transfer AC power from a voltage level to another voltage level. Transfer AC power, not DC power. So no DC power can be transferred using transformer. DC, I mean the pure DC. However, if you make some modifications for the DC to make it like variable, so in this case you can use transformer. If you will have the power electronics class, so you will learn one of the topologies of DC power supply. It's including transformer called push-pull transformer, so it can transfer DC, but only variable DC, not pure DC. However, in general, we can refer to transformer that it can transfer AC power, not DC power. So it transfers AC power from a voltage level to another voltage level. So what the meaning of voltage level? Voltage level means the RMS voltage level. So this is a basic rule why we use transformer. Sometimes we may use transformer between similar voltage levels, but this is just for the isolation. However, most probably it's not power transformer. Not power transformer means it's not transferring high power. So it's used for different purpose. So this is a general definition for our device. Also, a transformer consists of two or more windings. Two windings, primary and secondary windings, or sometimes the secondary winding can be many windings, not just one winding. So it could be 3-winding transformer, could be more. So it can have two or more windings, and these windings are coupled together by a mutual magnetic field through a magnetic core. So this is transformer, guys, or through a core. This core can be magnetic material, can be air. So we can have air transformer as well, not only with magnetic cores. So it has to have mutual magnetic field coupling all the windings of this transformer. In case of using magnetic cores, so we use ferromagnetic core. So the ferromagnetic core is nothing but the magnetic cores that we already described in the previous topics of magnetic circuits. So these ferromagnetic cores are used to provide tight magnetic coupling. Tight magnetic coupling means the coupling coefficient between the coils is relatively high. You know, guys, the ideal coupling coefficient is unity. And if the magnetic core is very high efficiency or having high value of permeability, so the magnetic reluctance will be very small. So in this case, the coupling coefficient will be high. And provide tight magnetic coupling and high flux densities. So it can produce high flux densities. Flux densities, guys, we used to have flux densities up to 1.2 to 1.4 Tesla for our electromagnetic devices. Such transformers are known as iron core. Iron because the material of the core is made of iron. The different types of iron as we discussed in the magnetic circuit topics. They are invariably used in high power applications. This is the power transformer. For sure, guys, we have different types of transformer. I assume that you already learned that in electrical circuits. So you have the pulse transformer, you have the current transformer, you have voltage measurement transformer. So we have a lot of types, guys, of transformer, but in our class, then this course is related to high power. So we will focus on the power transformer. So we use the power transformer in high power applications. Also, besides magnetic core, we may have air core transformers, as we mentioned. So the air core transformers have 4 magnetic coupling and are sometimes used in low power electronic circuits. However, sometimes, guys, we may need to use these air core transformers in some applications, but this is applications, let's say, for abnormal conditions, not for the normal conditions. Abnormal conditions means like fault condition. So assume that we are using transformer to transfer the power, so we will use the regular core transformer. But if you are using a transformer in a circuit breaker, so the circuit breaker is working for working to disconnect any fault and protect circuits and persons. So in this case, you can use a transformer inside a circuit breaker, but this transformer is going to be air core transformer. Why? Because for any core transformer, guys, if the current is relatively increased to the normal ratings, so the core may be saturated. And if the core is saturated, you will lose the function you need of this transformer. You don't have any more reflected value to make the circuit function, which means we cannot use magnetic core transformer for such case. So sometimes we may need air core transformer, but this is for abnormal conditions, not for normal operation. And in our course, guys, we are focusing on the normal operation of transformers. So all of our discussion in this topic will be on the magnetic based or magnetic core based transformer, not the air core transformer. Here, guys, we have an example of where we can use the power transformer in our electrical power network. Assume that you have this power network, 3 stages, as you can see. We have generation, we have transmission, and then we have distribution. So for the AC generation stage, regularly we generate the volt in small, not very small, not low volt, but small high volt magnitude. Like as you can see here, we have 30 kilovolts. So 30 kilovolt can be classified as medium or relatively high volt. And the first transformer you can see, so this is a single line diagram for a transformer. So the single line diagram here for this transformer is representing transformer transfers power from 30 kilovolt to 500 kilovolt. So this is called step up transformer. Step up transformer. So this is stepping up the volt from 30 kilovolt to 500 kilovolt. What this number 30 kilovolt represents here? So this represents the 3-phase line-to-line RMS value. So any number in 3-phase devices is referring to the coupling volt, and the coupling volt all of the time is line-to-line, whatever the connection. It could be Y, it could be delta. So all of the time this represents the line-to-line value and its RMS value. So 30 kilovolt line-to-line to 500 kilovolt line-to-line. So this is the first step here. So we step up the volt to 500 kilovolt. Then we transmit the power to another location. Most probably this is going to be long distance. It could be hundreds of miles. And after that, we have what's called distribution network. So the distribution network, guys, is distributed the power between loads. What are the different types of loads? It could be domestic loads with voltage or relatively low voltage values, like 120 volt, for instance. So this is the smallest value we may have, but most probably 120 is going to be line to neutral or single phase, not 3-phase. Okay. So we can, if you need a real value, let me replace this one here instead of 120 and make it 240. So 240 is reasonable line-to-line value we may have in our network. Okay, so this is the voltage level we may have now. So a question, or a first question, why we have many levels in the distribution network? The answer is we have different loads with different voltage levels. So domestic loads can have 240 line-to-line volts, and factories may need 44 or 4.6 kilovolts. So most probably these distribution networks are supplying loads with high power. So if you have a factory takes several tens of megavolt ampere. So 50 megavolt ampere, for instance. So this is huge power to be supplied from a transformer of 240 volt or 4.6 volts. So we may need the 44 kilovolt, okay, or higher 13 kilovolt, for instance, 13.8 kilovolt. So this is, guys, the concept. If you have high power load, we use relatively high volt to supply this type of load. So you may find different voltage levels in the distribution network according to the load requirements. The second question is, why, from the beginning, why do we use step-up transformer here? Why not moving the first level of volt required? So first level of volt required for a factory, it may be 44 kilovolts. So why not transferring the 44 instead of stepping up and stepping down again? The answer is, we use the high level or the high values of volt here in order to reduce the amount of current during the transmission. So definitely, guys, power will not increase during transmission. It could reduce because you will have losses during transmission. So if you assume that you have, for instance, 1 gigavolt ampere, 1 gigavolt ampere to be transferred. So this 1 gigavolt ampere, we can transfer this 1 gigavolt ampere through the 500 kilovolt, for instance, or maybe higher. So why? In order to reduce the current. So if you reduce the current during transmission, you know that the power loss on the transmission line, any power loss, guys, is represented by I square R, the copper loss. So copper loss in any windings or devices is summation of I square R. So the cables or transmission lines have resistances, and the power loss across these resistances is I square R. So if the current is relatively high, the power loss would be very high. For that, we do prefer to use high voltage levels in the transmission or before of transmission in order to reduce the amount of current transferred. And at the same time, guys, this would reduce the cross-section of the cable or transmission line used. Because if you need high current, for sure the cross-section area of the cable or the transmission line has to be high cross-section area in order to transmit this high current. So this is very important, guys, to understand the feasibility. Why do we use transformer? Okay. Nice. So this is a simple network just to represent the different transformers. So we have here step-up transformer. We have a step-down transformer. This is also step-down. This is another step-down transformer. All of these transformers are used in our power network. In this photo, guys, you can see a high power transformer used in a power plant. This is a 24 to 30 or to 345 kilovolt transformer. So this transformer, guys, is called generating transformer. So it's used in the generation stage. So after the generator, the volt of the generator is 24 kilovolt, and we step this up to 345 kilovolt in order to transmit this volt. So you can find here the 3 bushings of the transformer that connect this transformer to transmission line, to 3-phase transmission line, and these are the high volt side. By the way, the height of this transformer could be like 4 meters. So it's big transformer, okay? So we don't have a reference here close to the photo, or the photo is not that clear. I'm not sure if this is here a person beside this transformer, but if you can imagine, the person beside the transformer can be just at this length here, guys. So or a bit bigger. So this could be even more than 4 meters. This could be like 7 meters, something like that. So we have very huge transformers, guys, in our power plants. Later on, I'll show you the real construction of the transformer inside the transformer. What are the different parts we have in the transformer and how to protect the transformer, but this may be by the end of this topic. Then let's start, guys, in the practical transformer. Okay. So what is the practical transformer? Practical transformer compared to the ideal transformer. So the ideal transformer we discussed, or you know about it from the electrical circuits one. So the ideal transformer has no losses and it transfers all of the power from the primary side to the secondary side. And you know the ideal transformer ratio, which is V1 divided V2 equals N1 divided N2 equals I2 divided I1. So this is a well-known relation of the ideal transformer. But for the actual transformer, guys, what is the equivalent circuit and what are the parameters we have? So let's start, guys, with the practical transformer because I know all of you are familiar with the ideal transformer. So practical transformer, guys, it will have practical windings, which means these windings for sure will have resistance. And this resistance, guys, can be shown as a lumped quantity in series with the winding. So for any inductance, guys, so the coil, guys, you know the coil is nothing but some windings or some wires. These wires are wound around a certain core or in a certain way to form an inductance. So this wire, guys, for sure, it has a resistance. So you know for the resistance of any wire, it's rho L divide A. Rho L divide A, which is the resistance of this wire. So for any inductance, guys, you will have what's called equivalent series resistance. Equivalent series resistance. So in our transformer, guys, for sure, you will have equivalent series resistance for our transformer, for our windings. So in this case, we will have some copper losses and we will make like a series resistance with the inductance in order to represent this type of equivalent series resistance. Okay, this is one thing. When currents flow through the windings in the transformer, they establish a resultant magnetic or mutual flux. So for any current, guys, moves in inductance, you know that if you have many inductances together exist in the same or close to each other, so this would make some this will make some mutual coupling between these inductors, and this will cause magnetic flux or mutual magnetic flux. Okay, so let me write down here, guys, the relations we just mentioned. So I mentioned that for any resistance equals rho L divide A. Rho is the wire resistivity, L is the length of this wire, and A is the cross-section area of this wire. So this is the resistance of any wire. So this is resistance. And for any inductance, we will have ES R, which is equivalent series resistance. So by the end, any inductance like that can be represented by inductance and series resistance. So this is the inductance, and this is the equivalent series resistance of this inductance. Okay. Okay. Let's continue the point of the magnetic flux. So for any coupled coils, guys, as we mentioned, like that, we have here coil 1 and coil 2, and these coils are wound around a transformer core like that. So as you can see here, guys, you will have flux moving inside the core, and this is called linkage flux. This is called linkage flux. Okay. And also, you will have what's called leakage flux. What is the leakage flux? The leakage flux that will rotate around the inductor in the air gap without moving in the magnetic core. So this is called leakage flux. So the linkage flux is the useful flux that will transfer the power between primary and secondary. However, the leakage flux here, guys, will be representing the leakage inductance. Leakage inductance. So you have now two inductances, guys, L1 and L2, which are the leakage inductances, depend on the leakage flux. So for leakage inductance number 1 of the first coil, we will have N1, which is number of turns of coil number 1, phi L1, which is the leakage flux of the first coil, divide I1. N phi divide I equals L. So this is the inductance or the leakage inductance of the first coil. On the other hand, the second coil, the secondary side, will have also another inductance, depends on the leakage flux of the second coil. So we will have now L1 and L2. And since we are going to solve all of our questions in frequency domain, not time domain, so we will convert every inductance to reactance. You know that reactance is nothing but omega L, and omega is 2 pi F. So 2 pi F L1 is XL1, and XL2 is 2 pi F L2. So we can replace now the windings of the first coil by the R1, which is the equivalent series resistance of the coil itself, and XL1 is the leakage inductance of the primary winding. So this is now our impedance of the primary side. And for the secondary coil, we would have the same. So we have leakage inductance and the equivalent series resistance of the secondary side. And the part in between here, guys, which represents the magnetic coupling between the primary and the secondary, is nothing but an ideal transformer. And for this ideal transformer, if you have here E1 and E2, I can say E1 divide E2 equals N1 divide N2. So this is now an ideal transformer. We can consider this as a practical circuit, but we still missing small things. We will discuss it right now. So what are we missing? Actually, in practical magnetic core having finite permeability, a magnetic current IM is required to establish a flux in the core. So for any core, guys, we mentioned this before in the magnetic topics, you need to establish the flux in your core. In order to establish this core flux, you will need some currents. So this current is called the magnetization current and referred to as IM. This effect can be represented by a magnetizing inductance Lm. So we represent the magnetization in order to establish the flux in our transformer by this branch here. So what is this branch? The first side of the branch here on the right hand side is representing the magnetization inductance Lm, and we can represent this in frequency domain by Xm. So this is going to be the magnetizing reactance of the transformer. And at the same time, guys, for any core, we discussed also this in the magnetic topics, we have what's called eddy current loss and hysteresis loss. And the summation of these two losses is referred to as core loss. So in order to represent the core loss as well in our transformer, we represent this by a resistance. You know, guys, the only element in electricity that can represent power is resistor. Whatever this type of power, is it power gained or power loss? So by the end, this has to be a resistor. Okay, so in order to represent the core loss in our transformer, we can use this core resistance. So this core resistance is a virtual resistance, which means we don't have physical resistance inside a transformer called core resistance, but this resistance can be calculated or identified from the core loss of transformer. Okay. Later on, we will discuss how to identify all of the parameters of our transformer. Now, this is, guys, a practical transformer. This is the exact equivalent circuit of a practical transformer. One can say, where are the three phases? This is a very good question. So actually, this is, to this point, guys, this is still single phase. So as we described in the beginning of our session, we will refresh your knowledge firstly and review the single phase transformer. And after that, we will switch to three-phase transformer. So to this point here, we are still discussing the practical single phase transformer. So we have a single phase circuit. However, when we start discussing the three-phase transformer, guys, we will discuss the three-phase transformer as three single phase transformers. So this circuit will have three or will be repeated two more times for the other two phases. So if this is phase A, you will have another two circuits like that for phase B and phase C. But for three-phase transformer, we will not draw the complete three-phase circuit because it's symmetrical circuit. So all of our devices in this course, guys, are going to be symmetrical or balanced loads. So which means the three phases are identical. So you can just use a single phase and calculate everything and then modify your relations to get the three-phase values. This is the strategy that we will use in our three-phase machines in this course. So this is now a practical transformer equivalent circuit. And we call it exact equivalent circuit. Exact equivalent circuit. Since this is exact, guys, we will have some approximation. What are these approximations? We will discuss it, but before of going to the approximations, in this circuit now, guys, if you would like to calculate I2, sorry, this current here, assume this current is IX. What is the relation between IX and this current here, I2? So this is now ideal transformer. In order to move parameters or refer the parameters to the other side, we can use the ideal transformer relation. I'm going to write it here right now. So E1 divide E2 equals N1 divide N2 equals I2 divide I1. You know, guys, also, if we refer a current to another place, it would take the same subscript but with a prime. So if this is I2, the output current here, so we can say the input current here is I2 prime. So we can say Ix here is I2 prime. How can I get the Ix or I2 prime? From here. So I2 prime is representing actually the input current, which is referred to here as I1. So I can say this is here Ix instead of I1, okay? Because we have another I1 here in this circuit. So I can say from here, guys, Ix, which is I2 prime, equals I2 times N2 divide N1. And N2 divide N1 is 1 divide the turns ratio. So I can say I2 divides A, where A equals the transformer turns ratio, which is E1 divide E2 or N1 divide N2. So this is the way, guys, how can we make transferring. I know you already learned that in electrical circuits too, but this is just to refresh your knowledge. So I'm gonna transfer now every parameter from the secondary side to the primary side. So referring using the relation we mentioned now, we would have E1 equals E2 prime. We would have XL2 prime, R2 prime, and I2 prime. What are the values of everyone? So I2 prime, we just derived this in the previous slide. R2 prime is R2 times A2. Sorry, times A square, not divide. We mentioned before, guys, the voltage or the voltage transfer, let me write that, respect the side. Respect the side that it will be transferred to, which means I'm moving now from the secondary side to the primary side. So I would like to get E2 prime. If I would like to get E2 prime, I would respect the side that I am moving to. So I'm moving to the first side or the primary side. So I will multiply E2 times the first side turns ratio divide the secondary turns ratio. So by this way, I respected the side that I'm going to. The impedance will respect the ratio, but it's gonna be ratio square because impedance is V divide I. So in this case, if you would like to get R2 as a function, R2 prime as a function of R2, so we can say R2 prime equals R2 times. It will be transferred to the primary side and it respects also, so we would start with N1. Divide N2 and impedance is square. So N1 divide N2 is A square. So we can say R2 prime equals R2 times A square. And similarly, X2 prime equals X2 times A square. The only term that will not respect the side which is gonna move to is the electrical current, I. So moving I from the secondary side to the primary side, it will multiply times N2 divide N1. So it will not respect the ratio. So in this case, we can say I2 divide A. So E or V or E or Z, we multiply times turns ratio or turns ratio square in case of impedance and turns ratio in case of voltages, but current we will divide. This is when we move from the secondary side to the primary side. And if you have impedance in the load side, so you would transfer the impedance by the same way. However, in transformers, most of the time we will not aware of the impedance. We will be aware of the load power. So the load power will be described by means of volt ampere and power factor. Volt ampere is the S and power factor. Sometimes active power and power factor. Okay, so this is the way how to represent the transformer loads. So the circuit that you can see here, guys, is the exact equivalent circuit referred to the primary side. Exact equivalent circuit referred to the primary side. Okay. Let's make some approximation to simplify the circuit analysis. A first approximation, guys, can be the voltage drop across R1 and XL1, which is the primary impedance, is relatively small. So if we go back one slide here, this impedance, guys, is a small impedance. In this case, the voltage drop across this impedance will be very small. So what we can do is we can neglect the voltage difference between this point and this point and move this branch to the other side here. How this helps to simplify the circuit? Let's see. So if we move the R1 and XL1, so we would have now R1 and R2 prime here. Let's refer to this term by R equivalent 1. And XL1 plus XL2 prime, let's refer to this term by X equivalent 1. So R equivalent 1 or X equivalent 1 means, equivalent means total, primary and secondary. 1 means this term is referred to primary side. So the subscript 1, all of the time, guys, refer to that everything is referred to primary side. And X equivalent 1 is the same. So this is equivalent of the overall reactance of our leakage inductance, and 1 is the referred to primary side. So we can say now Z equivalent 1 equals R equivalent 1 plus J X equivalent 1. So this is the equivalent impedance. How this approximation simplifies the equivalent circuit? If you would like to get this current right now, guys, how can you get this current? So simply, you can use the same supply volt here, V1. Correct? Actually, most of the time, I2 will be obtained from the load side. So I2 prime will be calculated from the load data. But if you would like to make circuit analysis, in case of the previous circuit here, you would have this current. So this current I2 will be known. However, you don't know the volt of this point, which means you have to make some circuit analysis, like nodal analysis, or make loops like that. You have loop here, and you know the current of this one. So it's 3 loops, but 1 current is known. So by the end, you will have 2 equations. However, for the time being here, if you know this current, so you know the volt here, so you can simply calculate the current here because the volt is applied directly to these 2 parallel elements. So we can say IC1 equals V1 divided RC1, and we can say IM1 equals V1 divided XM1. So you will have this current, and that current, so you can easily get I1. So this small modifications here, guys, could simplify the circuit in order to calculate everything. This is a first approximation. A second approximation actually is going to make it very easy. If you compare between this circuit you can see here and the previous one, you will find that we don't have the magnetization branch. What's happened to neglect the magnetization branch, or is it feasible or not? So if the transformer, or sorry, in a transformer, the excitation current or the exciting current I phi is a small percentage of the rated current of the transformer. How much? Actually, it's around or less than 5%. So if you neglect this current, so simply we can say now our circuit is going to be just the equivalent impedance of the transformer. And this is V1 and V2 prime. So this is the approximation referred to primary side, and this is referred to secondary side. Okay, guys. So this is a second approximation in our circuit. Okay, now, so I think the determination of the equivalent circuit parameter, we may need to test or to discuss this in the next session, guys. So let's make this in the next class. So in our class today, let me just review again. What we discussed is we started firstly with the definition of the transformer. We define the different parameters of the transformer, what the meaning of resistance we have in the circuit, what the meaning of leakage reactance we have in the circuit. We drive together the exact equivalent circuit, and we make referral for our circuit to the primary side. And then we made two assumptions to have two approximated equivalent circuit. In the next session, we will start with the parameter identification of transformer. Thank you so much.